Hello, everyone. Welcome to the world of energy where work meets motion. So, here's a fun thought to start. Have you ever wondered why a speeding car has energy? Or why the faster something moves, the more energy it has? Well, it's all because of kinetic energy. This is the energy an object has due to its motion. Let's say you're driving a car. You know that the faster you go, the harder it is to stop, right? That's kinetic energy at work. The faster the car goes, the more energy it has. The formula for this is K equals 1/2 mv squared, where m is the mass of the car and v is its velocity. The faster you go, the more energy you need to stop, or in other words, the more work has been done on you. But hold on, why does it matter how much force is applied to an object? It's simple. Force is what causes changes in kinetic energy. So if you push something, you're transferring energy into it. That's how we can go from a standing car to a speeding one. Pretty cool, right? Now, let's get a little deeper. We've got kinetic energy, and we know force is connected to it. But what if the force acting on our object changes while it's moving? What if it's not constant, like when you're driving on a bumpy road and the force you feel keeps changing? Well, in that case, we have to talk about how force affects the change in kinetic energy at any instant. Here's how we do it. We differentiate the formula for kinetic energy, dk over dt equals mv dv over dt. Now, dv over dt is just the acceleration, which we already know from Newton's second law. So, when we substitute F equals m times dv over dt, force equals mass times acceleration, we get something cool, dk equals F times dx. This means that the change in kinetic energy is directly related to the force applied over the displacement. The further you push, the more energy you transfer into the object. Think of it like this. You're playing a game of pool. The harder you hit the ball, the more kinetic energy it gains. Force is what gets it rolling, and the more force, the more energy. Isn't that neat? Alright, so we know force changes kinetic energy. But what if the force isn't constant? Think about a sled sliding down a hill. The force of gravity is pulling it down, but as the sled picks up speed, the resistance from the snow, the force acting against the motion, starts increasing. In this case, we need to add up all the little bits of work done by the varying force. And we do that using an integral, fancy math talk for adding up all those tiny changes. The total work done is the integral of the force over displacement, kf minus k equals the integral from 11 to xf of f of x, dx. In simpler terms, the change in kinetic energy is the total work done by the variable force from position 11 to xf. Think of this like driving on a bumpy road. The force changes as you go over each bump. So, we need to sum up all these small forces to find the total work done. This gives us the change in the car's speed, the work-energy connection. Now, let's take a moment to think about the nature of the work-energy theorem. Unlike Newton's second law, which works with instantaneous forces, the work-energy theorem deals with the total work done over a certain path, not at a single point in time. So while Newton's law gives us the acceleration at a specific moment, the work-energy theorem focuses on the overall energy change. It's important to note that this is a scalar relationship, meaning it doesn't give us any direction information. It's simply saying, here's how much the energy changes from point A to point B. The work-energy theorem can be extremely useful in many real-world applications because it lets us calculate energy changes without needing to track every moment of force, and that's where the power lies. Let's bring this to life with an example. Imagine a block moving along a rough surface. It starts off with a speed of 2 meters per second and there's a retarding force acting on it as it moves. The force is proportional to the inverse of the distance moved, so the force gets weaker as the block travels. This is exactly the kind of problem where the work-energy theorem comes in handy. We know the initial velocity, and we also know the retarding force, but how do we figure out the final speed after it travels a certain distance? Well, that's where the work-energy theorem comes in. It's the perfect tool for solving this problem because it allows us to relate the work done by the friction force to the change in kinetic energy. Let's break it down step by step. Let's walk through it. First, the initial kinetic energy of the box. It's simply K equals 1/2 m(I) squared equals to joules, and we know the initial speed is 2 meters per second. That gives us 2 joules of initial kinetic energy. Now, to figure out the final speed, we use the work-energy theorem. We need to integrate the force over the distance traveled to find the total work done. The force given by f of x equals minus k over x is integrated over the displacement from 0.1 meters to 2.01 meters. This gives us kf minus k equals the integral from 0.1 to 2.01 of minus k over x dx. After solving that, we get the final kinetic energy to be 0.5 joules and the final speed of the box is 1 meter per second. This shows how the retarding force reduces the boxer's kinetic energy, and we just calculated it without needing to track the boxer's speed at every moment. Pretty slick, right? To wrap things up, we've seen that the work-energy theorem provides a simple, yet powerful way to relate the work done by a force to the change in an object's kinetic energy. This theorem isn't just about abstract formulas, it has real-world applications. Whether you're calculating the motion of a car, a rocket, or even understanding how friction slows things down, the work-energy theorem is at the heart of it all. Remember, it doesn't matter if the force is constant or varying, the principle remains the same. The change in kinetic energy is equal to the total work done by the forces acting on an object. So next time you're pushing something or stopping a moving object, just think about how the energy changes and how it all ties back to the forces you apply. I hope this clears up how forces and energy work together. Remember, whether you're speeding up a car, stopping a bike, or even understanding how a roller coaster works, it's all about the work-energy theorem. See you next time with another exciting physics concept.